All right. Hello, everyone. I'm Tuan, as you know. Today I'm going to talk about the paper called BPR, Bayesian Personalized Ranking from Implicit Feedback. This one is a baseline for Agnes paper just presented earlier. This paper published in UAI 2009. And okay, let's start. Come.
Turn it on.
Okay, it's working now. So who doesn't know BPR?
Oh, lot of hands.
Who doesn't know BPR? Okay. So no one knows BPR.
No.
Okay. So do you know logistic regression? Do you know logistic regression? All right. Okay, so as the paper mentions, right, we are dealing with implicit feedback. The type of feedback that we receive is, for example, click or view, a user view the items, right? So they don't explicitly express their preferences, but implicitly, somehow we imply that they prefer the items that they view over the one that they don't. So in this particular case, we can actually transform it to a binary matrix where we have those are the user item clicks matrix, then you can actually binarize it. So the missing value, you just assume that is to be 0. This is the way that the NCR paper, the data that the NCR paper learned from, but they learn the log loss to they minimize the log loss. So in this BPR framework, they do it differently. The way they do is actually from the same matrix, you gonna have somehow call is they actually try to preserve the order. So for each of the user here, let's say we focus on these parts, right? So we have this particular user 1, and this you observe that this user view this item 2. So then actually you can transform, for this particular user, you can transform to item matrix, where it's expressed that this user prefer item 2 to item 1. And the other way around is also true. So you actually can transform the original data to the new form of data. In this one, you have pair data, user item, and then in the new form of data, you have triplet data, user, positive item, and negative items. So this is the type data that we are dealing with now. So what is Bayesian? What is personalized? What is ranking? That is the name of the framework. So I will start answering from bottom up. It's ranking because it's trying to preserve the order, the ranking order of the items given particular user. So this particular user, the item I, he prefers item I to item J, so we preserve the ranking. Personalized means that we learn for each of the user, we have the model for that particular user. So actually this one is a form of logistic regression. Each of the user, you're gonna have his own logistic regression. Input a pair of items, positive item and negative items. You want to output, if that is the correct pair, means the positive, negative, then it's gonna give probability of 1. The other way around is gonna give probability 0. So that is the logistic form. So this is the sigma logistic function. It's Bayesian because it's follow the Bayesian rules in the form of that instead of maximizing the likelihood, they're maximizing a posterior, and they assume that the parameters of the model is from a standard Gaussian. So then they gonna, instead of maximize the likelihood from data only, they maximize the posterior based on this prior. So that is how they emphasize that Bayesian. So this is how the framework called Bayesian personalized ranking. So we already get the idea of the framework. The main part is actually about how you learn this function. So given the framework, how you learn this particular function. So now we come to the part of learning model with BPR. So BPR is a framework. So with BPR, you can learn multiple models. It depends on how you actually learn the function to output a score of a triplet, user, item, positive item, and negative item. So this is the form, right? So given a pair of user item, positive item, and negative item, you're gonna give the probability whether this user prefer the item I to item J, and this function, the function x uij here, you can actually decompose it to this particular form. This is one particular form. For example, is it going to give a scalar score? So you're going to do minus. So this one, for example, this user I use u item I and u item j. So there are two scores. So this particular user is going to give two scores for these two items, and then you want to maximize this score, the subtraction here when this is a true pair of positive and negative. So then it's going to maximize this probability. So this is a simple form of this particular function. So in the paper, they propose two ways to learn. Actually, it's two variants of the models that learn under this BPR framework. The first one, they use metric factorization to learn the interaction function. So metric factorization, as Angelis presented earlier, is so actually you can compute the score of user item based on inner product here, as earlier. So effectively, this one you can actually give a score for between user and one particular items. So then you map this function into this particular form. You get a score, then you back to here, then you get a probability. Then you can optimize the model. They propose another one variant of adaptive k nearest neighbors. So in this particular one, they actually the score between user to the item is equal to sum of the score of that particular item to all the positive items that user have observed before. So you want to compute the score of this user to these particular items. You look back to the history of this particular user. User already views some other positive products. So then you're gonna, for example, one form of score, you actually measure the similarity between these particular items to all the positive items of that particular user. So then it's gonna give the sense of how likely this user gonna like that particular item, depending on the similarity score, for example. Optimization is done through the gradient base. So is effectively this is the derivatives of the logistic function, and then you only need to care about the gradients of the score function. Then you plug into this particular framework, then you use the stochastic gradient descent, and then you can optimize the parameters of the model, theta of the model.
How do you compute CIL?
CIL is the parameters. In this particular case, you actually can, so it can be fixed, it can be learned. So if fixed, right, you have some feature, item feature, for example, then this CIL is the similarity score between two items. Okay. So if you want it to be adaptive in the sense that you want to learn that particular score, so you initialize it randomly, then you fit into the data, and then you actually update. So after you learn the model, you actually have the score between a pair of items. So the C matrix is the item matrix. Between two items, there is a similarity score. So after you update that, you learn the model, then you have the matrix, the learn matrix. Then in the future, when you predict, you want to predict between each user and this item. Then you look back to the positive items of that user you know, then you compute the score between that particular item and the positive items of that user. Then it's going to give you the score of that user and the item you want to predict.
So basically, it's the sum of the estimated score, right?
Yes, so this is the set, the IU plus here is the set of positive item of this particular user.
Yep.
So you actually just sum up the score of this item and the items that you have been viewed before.
Right.
How do you compute this for the positive item?
Positive item you know from the training data. So you know that particular user.
So it's the same formula. Did you need to exclude that item out of the
Yeah,
positive
you
set?
exclude that, right? So L is not I. So this particular, for example, you know that this this item, right? So this item, this user view this item, right? So you look back to the history of this particular user, so you see the set of I you plus here, except I. So you compute with the similarity between this particular item and the positive item of that user.
Okay, let me guess. The difference is from of the left and from the right stuff. The left they just take the inner product, and the right they just care about the positive item only. Right?
It's okay. I think I should put more notation here. So this actually, so the this factorization part is easy, right? So use the item you to factor then you do your products, right? In this particular case, so the notion, the score between the user to the item is equal to the score of that the positive set of that user to that item. So how similar this item? So in some sense, how similar this item to the set of the positive item that he had viewed before. So it's give high score, then meaning that this implies that this particular item is very likely that this user gonna favor this one. If the score is low, meaning that it's not likely that he's gonna prefer this one. So it's a bit bridging between the set of positive item of the user to that particular item. Okay, Maxim's back. Thank you. Up to now, no question, right?
Let me just ask you a few questions.
Ask you a few questions.
Up to now, we did after those questions.
Okay.
So there's one. I think it's very interesting analysis in the paper is that they derive the analogies between the BPR objective function to the AUC metric. So BPR actually directly optimized for AUC. So it's all right. We're gonna talk more about that. So effectively, this is AUC. This is the AUC stands for area under the rock curve. So this is the area under the rock curve. This is the rock curve. So AUC is the metric to measure the discriminative quality of a binary classifier. So as we discussed earlier, right? So effectively learning BPR model is that you are learning a logistic regression for each particular user. So you can imagine that each particular user you have a binary classifier given a pair of items that you actually classify as whether it's a true positive pair or not. So actually for logistic regressions, right, the binary classifier, you actually have the different threshold probability. So above that threshold, you're gonna decide that example is positive. Below that threshold, you're gonna decide that particular example is negative. So given the different points of the threshold, then you can actually plot the curve, the rock curve here. Then you can actually measure the area under the curve. So the higher the value, the better the in the discriminative quality of the binary classifier. So the best you can achieve is actually this point. So you actually have AUC equal to 1. So easier to imagine. We actually give some example here. For example, so AUC measure based on the true positive rate, meaning that even the set of positive examples, what is the success, the number of correct examples you can make among the positive examples. The 4 positive rate measure that how many incorrect example among the negative example that you have made. So this one, let's say this is true negative, this is true positive. So this is, let's say it's a balanced data set. So this is a perfect classifier where you can actually discriminate between the two sets, positive and negative. There's no overlap. So you get AUC equal to 1. In this case, there's some overlap. So this is the capacity of your binary classifier. You can actually not distinguish this part. You can only distinguish this easy part. But when you go to this part, you actually cannot distinguish between these two sets. So either you adjust the threshold, you're gonna if you increase the true positive rate, then you're gonna increase the false positive rate as well at the same time. So this is the best you can do, which is AUC equal to 0.7. In this case, it's a random guess. So effectively, you have no chance distinguishing between the positive example and negative example. So you just do randomly. Given that the data set is balanced, then the threshold is 0.5, then you get AUC 0.5. This is random guess. So actually, this slide represents the random guess. So if you do better than random, this one you do better than random, this one you do worse than random. But worse than random means that you reverse it, and you do better than random. Okay, so in the BPR frameworks, right? So as we discussed, that each particular user is actually a binary classifier in a sense. Then measuring AUC, we average across all the binary classifier per particular user, right? So we only need to care about one particular user. Then the AUC for the whole model is actually the average result across all the users. So this one is the formulation to calculate the AUC for one particular user. So as I discussed, the positive example of the triplet data here is the positive item and negative items. So that is one particular example. So in this BPR framework is a specific case where you actually have your positive example. If you reverse the order of the items, then you get a negative example. So actually, you only need to measure the 2 positive rate, then you actually can infer the 4 positive rate at the same time when you just need to reverse it. So then you only need to care about all the correct positive pair because it's symmetric. So then it's not actually the curve anymore, it's actually just this line of then you can actually just measure one point in this line. Then you can actually measure the AUC of the BPR. So we come to the evaluation of the BPR model. Well, you all know, right? I mean, they're gonna perform the best. Here, the only point I want to emphasize is that as presented to a variant, the metric factorization and the k-nearest neighbors. The metric factorization model actually seems to perform better than the simple nearest neighbors, nearest neighbor base. And in this particular case, for the Netflix data set, you actually, when you increase the number of dimensions, you actually achieve a very good result, like AUC 0.92, which is very high a measurement for ranking quality of the BPR model. So up to now, the metric factorization framework is effective, very efficient to compute the score. So the popular variant of the BPR model is still BPR metric factorization. Some key takeaways from the paper. So BPR is a learning framework for personalized ranking. BPR is nothing but the logistic regression for triplet data: user, positive item, and negative item. BPR optimizes AUC, and BPR is one of the foundations for recommended systems. So under this particular framework, you actually can build on top of that for other models. So it's a matter how you learn the function score between the triplet data, user, item, and positive item and negative items. Then you plug into this particular framework, then you can actually build on top of this one. So it's a very important concept in recommended system. It's similar to logistic regression to machine learning. Yeah, that's all for my presentation about BPR. Any questions?